Hello, this is the Chapter 15 homework solutions video for Physics 102B. Number 29 says, estimate the number of electrons present in a neutral 1 kilogram block of carbon. Before we get to the number of electrons, let's first think how many atoms there are in 1 kilogram. Carbon has an atomic weight of 12, and that means it is 12 grams per mole. So let's start with our given information that it's 1 kilogram, which is 1,000 grams, and let's figure out how many moles that is. So we have 1,000 grams, and then we have 12 grams per mole, arranged like we're doing a unit conversion, so the grams will divide out, leaving us with moles. That'll give the moles. We want to know how many atoms there are, so multiply by Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. And then, once we have how many atoms there are, we want to know how many electrons. So carbon, if it's neutral, has 6 electrons per atom because it's element number 6, atomic number 6. And so you can see as you look at these units, the grams and grams have divided out the moles and moles, the atoms and atoms, and it leaves us with electrons. So we have 3 times 10 to the 26th electrons. Number 32 says a plastic rod is rubbed with a cloth, and in the process it acquires a charge of negative 2.3 times 10 to the negative 8 coulombs. Did the mass of the rod increase or decrease, and by how much? It gained a negative charge, and remember electrons have negative charge, so that means that it gained electrons, so its mass does increase. And let's see how much its mass increases. We'll figure out how many electrons there are, and then multiply by the mass on each electron. So there's the charge. We're going to treat this like we're doing a unit conversion. We're going to multiply by 1 electron over negative 1.602 times 10 to the negative 19 coulombs. And that gives us 1.44 times 10 to the 11th electrons. That's how many electrons it gained. Now, if we want to know the mass, we'll multiply by the mass of an electron, 9.11 times 10 to the negative 31 kilograms per electron. And by the way, these are two constants that will be coming up much this semester, so you should know this. The charge on an electron, negative 1.602 times 10 to the negative 19 coulombs. You'll be seeing that number over and over again this semester, so it's best to commit it to memory. And also the mass of an electron is good to know, 9.11 times 10 to the negative 31 kilograms. So when we multiply by that mass, we get that the plastic rod has gained a mass of 1.3 times 10 to the negative 19 kilograms. Number 33, it's an exercise in using Coulomb's law. Two small charged balls have a repulsive force of 0.12 newtons. When they're at a distance of 0.85 meters, the balls are moved closer together till the repulsive force is 0.6 newtons. How far apart are they now? So we move them closer together. The force increases. And it even says that we're moving them closer together. So when we get to the end of this problem, we'll be able to check our answer, see if it's reasonable by it should be closer than the original distance. I've written out the given information. There's F0 and F1. There's R0 and R1 is what we want to solve for. And here's a good technique to use. You were introduced to this in the first semester of this class. We use Coulomb's law, F equals K Q1 Q2 over R squared. And let's separate out on the left hand and right hand of the equation the things that are changing on the left hand and the things that are constant on the right hand. So we've got FR squared equals KQ1 Q2. KQ1 Q2 stays on the right hand side, and we really don't care about those, so we're just going to say they are constant. FR squared equals some constant. And now that we know that relationship, let's come down here and say F1 R1 squared is F0 R0 squared. And then we'll solve for R1, go through the algebra, and you get R1 equals the square root of F0 over F1 times R0. Then we plug in the values, we get 0.38 meters, and we check, are they actually closer than they started out? And yes, they started out at 0.85 meters, and now they're just 0.38 meters. Number 37. Two ping pong balls each have a mass of 1.4 grams and carry a net charge of 0.450 microcoulombs. One ball is held fixed. At what height should the second ball be placed directly above the fixed ball if it is to remain at rest there? So the idea is we are going to levitate a ping pong ball. We're going to levitate it against the force of gravity acting on it. So here I've drawn a little picture here. We can do the force diagram on that top ping pong ball. The electric force of repulsion is going up, its weight is going down. And so let's use F equals ma, where acceleration is 0. So the electric force going up minus the weight going down equals 0. And we want to solve for the distance between them. So let's go to this next line. I've turned the electrical force to kq squared over r squared, and I've added mg to both sides of the equation. So we have this line. Let's continue to solve algebraically for r, and you get the square root of kq squared over mg, square rooted. And you can see I've plugged in the numbers here, and you should get 0.364 meters. Number 42. 3-point charges are placed on the x-axis as follows. 20 microcoulombs at x equals 0, 30 microcoulombs at x equals 0.5 meters, and negative 10 microcoulombs at x equals 1 meter. Find the net force on each point charge. We need to draw a picture here. So here I've drawn the picture with the scale. And we want to find the net force on each charge. Now, let's think about the charge on force 1. I'm sorry, the force between charges 1 and 2 is what I meant to say. And then we'll do the force between 1 and 3 and the force between 2 and 3. Let's figure out what each of these forces is. So the force between charge 1 and 2, and here I've shown it on the picture, it's going to be pushing charge 1 to the left. And why is it pushing it? Well, charge 2 and charge 1 are both positive, and so it's going to be repulsive. So the force of 2 acting on 1 is going to push 1 to the left. Also, right here in the middle is the force of 2 acting on 1 or 1 acting on 2. Remember, by Newton's third law, it's the same force, just different directions. So charge 1 is going to be pushing charge 2 to the right. So let's figure out what this is. It's the force of 2 acting on 1 or the force of 1 acting on 2. You can call them either one you want, but it's this. It's K, that Coulomb constant, times Q1 times Q2 over their distance squared. So we're going to use K. Now here I've very abbreviated, wrote it as 9 times 10 to the 9th. You should be more precise than that. It's 8.9876. So often in my notes and in the lecture, you'll see me doing that, 8.9876. I just, for brevity of writing, just abbreviate it as 9 times 10 to the 9th. Times, these are in microcoulombs, so 20 times 10 to the negative 6, 30 times 10 to the negative 6 coulombs. Divide by their distance, they are 0.5 meters apart, and you get that that force is 21.6 newtons. Let's move on now to see the force between 1 and 3, and that's going to manifest itself right here. The force of 3 pulling on 1, and here's the force of 1 pulling on 3. They're attractive because one is positive, the other is negative. And you plug those values in, you get 1.8 newtons. Now, if you plug in those charges exactly, you should be getting a negative sign, but we don't want that. When we apply Coulomb's law, we're actually going to plug in the absolute values of the charges. So even though up here, where my pointer is, I just wrote Q1, Q2, we always plug in just the absolute values. We're always going to get a positive number. So 1.8 newtons is what you should get. And then you do the force of 2 and 3 acting on each other, And since they're opposite charges, they pull on each other. Charge 2 is going to be pulled to the right. Charge 3 is going to be pulled to the left. But the force between 2 and 3, when you plug in their charges, divided by their distance, they are 0.5 apart from each other. You should get 10.8 newtons. Now, we haven't answered the question yet. All we've found is what the different forces are. The question is actually asking, find the net force on each point charge. So let's go to the next page. And this is where our picture is going to be necessary so we can see what directions things are going. Let's think about the force on charge 1. It is going to be the force of 1, 3, so the force that 3 is pulling on 1, minus the force that 2 is pulling on 1. There's a minus because they are opposite direction. Now, I'm calling the force of 1 pulling on, or 3 pulling on 1 positive, just because by convention we make going to the right, that's the positive x direction. I'm thinking of to the right being positive. So that's positive, force of 2 on 1 is negative, and we get negative 19.8 newtons I hat, which means it's 19.8 newtons pointing to the left. So that's the answer, the force on charge 1. The force on 2, let's look up at the picture, and we see that the force of 3 pulling on 2 is to the right. The force of 1 pushing away on 2 is to the right. They're both in the same direction. We're going to add them. So when you add those up, you get it's 21.6 newtons plus 10.8 newtons. So that gives us 32.4 newtons I hat. It's positive, so 32.4 newtons to the right. And finally, the force on charge 3, let's look at the picture. They're both in the negative direction. 1 is pulling it to the left, 2 is pulling it to the left. And so we're going to say, because they're to the left, negative force of 1 on 3 minus force of 2 on 3. And we get negative 12.6 newtons I hat, or we can say 12.6 newtons to the left. Number 43. 2-point charges, negative 25 microcoulombs and negative 75 microcoulombs, are held fixed exactly 1 meter apart. Where should a third charge be placed so that the net force on it is 0? Explain why the magnitude and sign of the third charge do not affect your answer to part A. Okay, so where should we put this third charge so the net force on it is 0? Let's think about all the different places we could put it. And let's imagine it's a positive charge. The question says, it tells us that the magnitude and sign don't make a difference. Let's just imagine a positive charge. And let's get things a bit more complicated and think anywhere in the space around. So getting beyond the one-dimensional line, let's just plop a positive charge right here where my pointer is. It's going to be attracted downward towards those negatives. Now, left or right is immaterial. The point is it's going to be attracted downward. If we put it below that line between them, it's going to be attracted upward. And if it were a negative charge, it would be repelled. But so anywhere that's not on a direct line between those charges, it's going to have a net force. So there are 3 regions we can contemplate. To the left of the negative 25 microcoulombs, in between them, and to the right of the negative 75. Well, if we put it here to the left, it's going to be attracted to both of them. So there's a non-zero net force. If we put it to the right, it's going to be attracted to both of them. So it's got to be somewhere here in the middle. Now, if we put it in the middle somewhere, then, as you can see where I've drawn this X, I don't know where it should be yet, but it's our job to figure that out. Then it's going to be attracted to the one on the left. It's going to be attracted to the one on the right. So we're looking for that place where the attractions are equal and opposite to each other. We need to find the distances between them. So let's break this down to the distance from the negative 25 microcoulomb. Let's call that X. And since those two known charges are a meter apart, then the distance between our mystery position and the negative 75 microcoulombs, we'll call that 1 meter minus x, or 1 minus x, so that together these two distances add up to 1 meter. And now we're going to let the absolute values of their forces be equal. So F1 equals F2, meaning the force that our mystery charge it's being pulled on by the negative 25 microcoulombs is equal in absolute value to the force that it's being pulled on by the negative 75 microcoulombs. Now let's use Coulomb's law. You can see I've expanded into Coulomb's law. I've written K times negative 25 microcoulombs times our mystery charge, divide by x squared. K negative 75 microcoulombs Q over that distance, 1 minus x squared. Now, usually when we're calculating forces, we do MKS units. So usually I'm turning those charges into 25 times 10 to the negative 6, and that 75 times 10 to the negative 6. But there's going to be a point in about a line or two where whatever power of 10 we're using is just going to divide out anyway, as you'll see in a minute. So let's see how we can simplify this. Notice that the Q's divided out. And so you can see, this is the part B question, explain why the magnitude and sign of the third charge do not affect your answer. Well, it divided out. And then we're left, and the K divides out also. Now we're left with negative 25 microcoulombs over x squared equals negative 75 microcoulombs over 1 minus x squared. And we can then divide out from each side of the equation 25 microcoulombs. So when you divide the left-hand side by, negative 25 microcoulombs. When we divide the left-hand side by negative 25 microcoulombs, it just leaves a 1 in the numerator. And when we do it to the right side, it just leaves a 3 in the numerator. So all that matters is not how many microcoulombs they are, but simply that those charges are a 3-to-1 ratio of each other. And now we're going from it being a physics problem to simply a math problem, an algebra problem. Let's solve this equation. So we can do what's called cross multiplying, if you want to call it that. 1 times 1 minus x squared equals 3 times x squared. And let's expand that 1 minus x squared to be 1 minus 2x plus x squared. Let's get this in standard form of a trinomial. So I'm getting everything over to the right-hand side. I'm subtracting x squared from both sides, leaving us with 2x squared. I'm adding 2x to both sides. I'm subtracting 1 from both sides. So we get 0 equals 2x squared plus 2x minus 1. And then it's appropriate to use the quadratic formula. So x equals negative 1 plus or minus square root of 3 over 2. That gives us one positive solution. We're going to go for the positive because since we're talking about distances here, it's clearly a positive solution that we're looking for. So we can plug that into the calculator and we get 0.366 meters as x. And now we have to see, what does that mean? X equals 0.366 meters. Well, we'll go back up to our picture and see this is what we designated x. X is the distance from that left charge. So 0.366 meters from the smaller charge. Number 47. 4 identical point charges of 5.6 nanocoulombs are placed at the corners of a square 0.25 meters on a side. Find the force acting on each charge. All right, so a bit of a two-dimensional problem here. What's going to be nice is that there is symmetry to this. All the charges are the same. It's a nice square. The distances are going to come out to be the same. As I've drawn the picture, I've labeled them charges 1, 2, 3, and 4. And what I'm going to do is find the net force acting on charge 1. And because of symmetry, what I hope you can see is that it's going to be the same answer for 2, 3, and 4. Meaning whatever's happening to charge 1, it's getting pulled on horizontally, it's getting pulled on vertically, and it's getting pulled on diagonally. The same thing is happening to charge 2. It's getting pulled on vertically, horizontally, and diagonally. Same thing's happening to charge 3. Same thing is happening to charge 4. There's perfect symmetry here. So all we have to do is find the net force on one of these charges. So let's figure out first what are all the different forces. So on charge 1, we can see that 2 is pulling on it. It's a charge of q, a distance of x, so kq squared over x squared. And we don't know what we do know what the numbers are. We'll plug those in at the end, but we'll just keep it in its general form now, kq squared over x squared. Now, there's the diagonal bit there. What is 3 doing to 1? Well, the force of 3 on 1 is k times q, so kq squared, divided by. Now, let's do some geometry here. You can use Pythagorean theorem to solve for that diagonal, but it's good to know that the diagonal of a square, the length of it, is the square root of 2 times the length of one of those sides. So it's x times square root of 2. So here I have in the denominator x times square root of 2. I've written it as square root of 2 times x, and don't put the x inside the radical. So square root of 2 times x. And then for Coulomb's equation, we're going to square that, and that becomes 2x squared. Now let's compare the force of 3 on 1 versus the force of 2 on 1. 3 on 1 is kq squared over 2x squared. 2 on 1 is kq squared over x squared, and that's also the force of 4 on 1. So I want you to see that force of 3 on 1 is 1/2 of the force of 4 on 1. So that'll simplify things a bit. Okay, now let's think about what is happening to charge 1. And I've drawn a force diagram here. Force of charge 2 on charge 1 is upward. It's upward because they are equal, or they are the same sign, so all of these forces are repulsive. So charge 2 is pushing charge 1 upward. Charge 4 is pushing charge 1 to the right. Charge 3 is pushing it away diagonally. So there's our force diagram. And charge 3 is pushing it up at a 45-degree angle, because that's the angle of the diagonal. Now what we're going to do, now that we have the force diagram, we're going to think back to chapter 4 of last semester, how we dealt with a force diagram like this. And so we're going to break it down into its x and its y components. So let's think about the x component first, looking at our force diagram. Well, it's the force of 4 on 1. Here, sorry about the writing here. I had written force of 1 on 4, and then I changed it to 4 on 1, but didn't completely block it out. That's the force of 4 on 1. Plus, we need the x component of the force of 3 on 1, and that's going to be the force of 3 on 1 times the cosine of 45 degrees. And so then we can, here I've started to do the force of 4 on 1, which up here is kq squared over x squared. And so I have plugged in those values. Again, I recommend, rather than the 9 times 10 to the 9th that I wrote here for k, use a more precise value, 8.9876. Very easy to remember, 8.9876 times 10 to the 9th. Okay, I didn't bother to write it out for force of 3 on 1, but you can do that. The force of 3 on 1 is 1/2 of the force of 4 on 1 times the cosine of 45 degrees. And here I've, yes, there I've done it. So when I plug in the values, it's 4.516 micronewtons plus, there's the 1/2 of 4.516 micronewtons times that cosine of 45 degrees. And it comes out to be 6.11 micronewtons. So what we've done here is we've solved for the x component of the forces. The y component of all the forces is the force of 2 on 1 plus the force of 3 on 1 times sine of 45 degrees. When you plug in all the values, you get 6.11 micronewtons, but maybe you don't even need to plug in all those values. You can see by symmetry that whatever's happening horizontally to charge 1, let's go down here. Whatever's happening horizontally to charge 1, exactly the same thing is happening vertically. And so they should be the same. So we get 6.11 micronewtons horizontally, 6.11 micronewtons vertically, and use Pythagorean theorem and you get 8.6 micronewtons as the net force acting on charge 1. And again, the question asks, find the force acting on each charge, but by symmetry of that square, it's going to be the same. We could have done those same calculations on any one of those charges, and it would have been exactly the same. Number 53, what is the electric field a distance 1 millimeters from an electron? So you need to be able to distinguish when it's asking about a force or if it's asking about a field. Now it's asking about the field. So the electric field, we use the capital letter E from a point charge. You should know this formula is KQ over R squared. And so we're going to fill in the values, and you should get 1.44 times 10 to the negative 3 newtons per coulomb. Number 54, I only ask you to do part A because I just want to keep these homework questions one-dimensional. Two positive point charges, each 15 microcoulombs, lie along the x-axis. One's at negative 0.15 meters, the other's at positive 0.15 meters, as I've drawn in the picture. Find the electric field at the origin, so at 0, 0. Okay, nice one-dimensional problem. What is the electric field? The total electric field, we're going to use the superposition principle. It's going to be the addition of those two fields. Now, let's draw a picture of the fields. The field from charge 1 points away from charge 1. It points to the right because remember the direction of a field is the direction that a positive test charge would be accelerated, so it would be pushed away. E2, a positive charge would be pushed away from charge 2, and so they're going to be opposite directions. So when we add those fields, E1 being positive and E2 being negative, then we get E1 minus E2. And so then we plug in the values KQ1 over 0.15 meters squared minus KQ2 over 0.15 meters squared. And so because they're exactly the same thing, they're going to be 0. And in this case, it didn't matter that they were both 15 microcoulombs because whatever their charges were, it just subtracts to be 0. Number 57. We're just going to do part A. For the electric dipole in example 15.7, compute the electric field at the location negative 15 and 0. So we have to go back and look at example 15.7. And if you go back to that example on page 342, it says the dipole lies on the x-axis. There's a negative 2.5 nanocoulomb charge at negative 10 centimeters, and so there I've drawn it there, and a positive 2.5 nanocoulomb charge at positive 10 centimeters, so I've drawn it right there. And you should, before doing this problem, you should go over example 15.7, and this problem is just kind of a redo of the example. And it's asking to compute the electric field at negative 15 and 0, so at this position right here. And let's think about what the two different electric fields from the two different charges are doing. Charge 1 is going to pull to the right, so the electric field points to the right. Remember, an electric field vector points in the direction that a positive charge would be accelerated. And at this position, a positive charge would be accelerated towards charge 1, because charge 1 is negative. The electric field of 2, well, since charge 2 is positive, it would be repulsive towards a positive charge. That's where my pointer's at. And so the electric field from 2 points away. It points to the left. So we have E1 pointing to the right, E2 pointing to the left. Let's solve for each of those. E1 is the Coulomb constant, 8.9876 times 10 to the 9th, times 25 nanocoulombs. So we have 2.5 times 10 to the negative 9 coulombs. And I have just done the absolute value there. That'll give the magnitude of the electric field. I already know the direction because we used the geometry and drew the picture up at the top. But so I've used the absolute value. Divide by its distance. It's 5 centimeters away, so 0.05 meters squared. And you should get 9 times 10 to the third newtons per coulomb. It's to the right, so I can say I hat. Electric field from 2 is the Coulomb constant times the charge. Again, I've used the absolute value. It's positive anyway. Divided by its distance, and we look at the picture, and we see that it's 25 centimeters. This position is 25 centimeters from the positive charge 2. And so there we go. And we get 360 newtons per coulomb. Now that is the absolute value. If we want to put it in vector form, we recognize from our picture that it's going to the left. So we'll say negative 360 newtons per coulomb I hat. And then using the superposition principle, the addition of those two vectors, it's E1, but then E2 is in the negative direction, so we'll say E1 minus E2, and we get 8640 newtons per coulomb. Because it's positive, we say to the right. As a vector, we can say 8640 newtons per coulomb I hat. Number 61 gives us a surface charge density of a charge plane, negative 1.5 times 10 to the negative 7 coulombs per meter squared. We want to figure out how many electrons there are on a square that is 1 millimeter on a side. So there it is, the Greek letter sigma for surface charge density, negative 1.5 times 10 to the negative 7 coulombs per meter squared. And we want to effectively treat this like a unit conversion problem. We want to turn it into electrons per square millimeter. And so we'll start with the given information of coulombs per meter squared. Let's turn those coulombs into electrons. So 1 electron over negative 1.602 times 10 to the negative 19 coulombs. That'll give us electrons per meter squared. Now, let's convert that to millimeters squared. We have the conversion 1 meter up top divided by 1,000 millimeters down below. But remember, we have to do square meters to square millimeters, so we need to square that to do 2 powers of the conversion. And in the end, you should get 940,000 electrons per square millimeter. Number 63. A pair of charged parallel planes are used to create a uniform electric field between the planes. The charge densities on the 2 planes are equal in magnitude but have opposite sign. Find the charge density on each plane if the electric field between them has a magnitude of 10,000 newtons per coulomb. All right, so we have an equation from the book, a formula that says in such a scenario between these 2 oppositely charged parallel planes, that the electric field in between them is the surface charge density divided by epsilon naught, that permittivity of free space constant. So let's solve for sigma. The question is asking find the charge density. That's what this is. Sigma equals epsilon naught times E. And then you just plug in the values given. So you get 8.85 times 10 to the negative 8 coulombs per meter squared. Number 65, assume that the hydrogen atom consists of an electron in a circular orbit around a proton with an orbital radius of 5.29 times 10 to the negative 11 meters. Question A asks, what is the electric field acting on the electron? And B, use your answer in part A to find the force acting on the electron. So the field acting on the electron is the field from the point charge that is the proton right there in the middle. And so the electric field from a point charge is K times that charge divided by R squared. So K I've written 9 times 10 to the 9th, but again, we're going to be more precise. 8.9876 times 10 to the 9th times the charge. Now, we're looking at the charge from or the electric field from a point charge. That capital Q, the charge we're putting in, has nothing to do with the electron, because this electric field is going to exist whether or not the electron is there. So we're talking about the charge of a proton. Now here it doesn't matter that much because a proton and electron have the same charge, but just to clarify, we are talking about the charge, the charge that the electric field is emanating from. So it's the charge of the proton divided by their distance given squared, and you get 5.15 times 10 to the 11th newtons per coulomb. Question B asks, to use your answer for part A, find the force acting on the electron. So it's going to be the electric field times the charge on the electron. I'm using the absolute value just because I'm looking for an absolute value answer here. Don't really care for positive or negative. We're looking for the magnitude of the force. So when we multiply by the electric field by the charge of an electron, we get 8.25 times 10 to the negative 8 newtons. By the way, you could have also gotten the answer from question B. You could have bypassed question A and just used Coulomb's law to find the answer to question B. Coulomb's law says it would be kq of the proton, q of the electron divided by r squared. You should get the same answer. Number 67 says 2 point charges lie on the x-axis, 0.25 microcoulombs at 0.25 meters and 0.16 microcoulombs at 0.75 meters. Find the place or places where the electric field is 0. Let's draw the picture first. And we have the first charge at 0.25, the second at 0.75. They're both positive charges. And so where would the electric field be equal to 0? And so you can think electric field vector points in the direction that a positive charge would be accelerated. And right here in the middle, a positive charge is going to be pushed away from the charge on the left. It's going to be pushed away from the charge on the right. So it's getting these equal and opposite forces. And so it's going to be somewhere there in the middle. Now, in contrast, if we were to put a positive charge out here to the left, it would be repelled away from both of them. So because it would feel a non-zero force, then that means there's a non-zero electric field. Same if we put it over here way out on the right. It would be pushed away to the right. So clearly there's an electric field out there. So it's going to be somewhere here in the middle. And we want to know where's it going to be. So let's just draw it in a random place right there. We have a sense that it's got to be closer. In order for these electric fields to be equal in magnitude, it's got to be closer to the weaker charge. So I've drawn it somewhere a bit closer to the 0.16 microcoulomb charge. I've drawn my electric field vectors. So charge 1, the one on the left, is pushing it. The electric field from it goes to the right. The electric field from the positive charge on the right is pushing to the left. And so you can see this, and we're looking for where E1 is equal to E2. So I've established the x as to be just the position on the x-axis. In order for us to apply the equations, we need to know the distances that we can plug into those denominators. So if this is at position x, then the distance between it and the left charge is x minus 0.25. And the distance between it and the right charge is 0.75 minus x. Now, if you had done x minus 0.75, because x is less than 0.75, you would get a negative answer. And so plug in, like make up a number such as 0.3 x equals 0.3. Just imagine, that's not going to be the right answer. But you can see how the distance from the one on the left should be x minus 0.25, and the distance from the one on the right is 0.75 minus x. Okay, now let's apply these equations. E1 equals E2. We're looking for where they balance out perfectly. Plug in the values into those equations, and the k's divide out. And now we're just going to solve algebraically. So I'll do the cross multiplying. So Q1 times 0.75 minus x squared equals Q2 times x minus 0.25 squared. And we're just going to go ahead and solve that algebraically. I'm not going to plug in the values of Q until I get a little further down in the equation. I'm expanding those binomials. So you can go through the algebra. Make sure you do this on your own. Don't just watch what I'm doing, but do it on your own. Make sure that you can do it, as with every homework problem in this class. And I've chosen now to apply those charges, 0.25 and 0.16. I didn't bother to do the powers of 10, so really in coulombs, those are 0.25 times 10 to the negative 6. This one is 0.16 times 10 to the negative 6, but those numbers then, in order to do the algebra, become a bit cumbersome. So essentially, I've just divided out the 10 to the negative 6. And we have 0.25 and 0.16. Now I've distributed those numbers, and we have on the left side, the right side. When you're doing it on your own, if you're following what I'm doing, you should get the same thing. And then I've simplified to get it into standard form. Finally, with this line down below, we've got a trinomial in standard form. And to solve it, if you have a graphing calculator, those work very well for solving an equation like this, or you can use the quadratic formula, but you should get 0.528 meters. That's x. And then we're going to check on, does this answer seem reasonable? So let's go up here and we see x, this position of 0.528 meters. Yes, it is somewhere in between those two, so that checks out. And also, it should be closer to the weaker charge. And so you can see, yes, it is. Number 71, a small bit of photocopier toner having mass of 3.5 times 10 to the negative 15 kilograms carries a net charge of 2e and has an acceleration of 0.5 meters per second squared. What is the magnitude of the electric field that causes that acceleration? All right, we've got our mass, we've got our charge is 2 times the elementary charge, we've got our acceleration, and let's use the equation. Remember that the force on a charge is the electric field times that charge. So that means the electric field is force divided by charge, and force is ma divided by the charge, and so we plug in those values and we get 5460 newtons per coulomb. Number 73, an electron moving in the xy plane has an acceleration of 3.25 times 10 to the negative 13 meters per second squared at a 30-degree angle above the x-axis. Find the electric field responsible for that acceleration. All right, an electron being a negative charge is going to be accelerated in the opposite direction of an electric field. So remember, something you've heard me say over and over again, that an electric field vector, it points in the direction that a positive charge would be accelerated. A negative charge goes in the opposite direction. So you look at my picture, if the electron's going this way, the electric field goes exactly opposite this way. So electric field is force divided by the charge, and force is ma divided by the charge on the electron. And as I wrote here, I just take the absolute value of charge. Whether negative or positive, that'll work itself out as we evaluate the diagram, the geometry of it. So we're finding the magnitude of the electric charge of the electric field. So there's the mass of an electron, the acceleration, divided by the charge of the electron. And so we get a magnitude of 185 newtons per coulomb. And you can see by the picture the direction it's going 30 degrees below the negative x-axis, which is going to be direction of 180 plus 30, so 210 degrees. Number 75. In a Millikan oil drop experiment, using oil with a density of 940 kilograms per meter cubed, a droplet with a charge of negative 3e is just balanced against gravity in an electric field of 11.5 kilonewtons per coulomb. What is the direction of the electric field? What is the size of the spherical droplet? All right, the direction of the electric field, that's the easy one here. So we think we've got this particle, this oil drop. It's got a charge of, it's got a negative charge on it. Gravity is pulling it down. In order to be levitated against gravity, it's got to have an electric force that's pushing up. And so then we think, what is the direction of an electric field that would make a negative charge go up? Well, negative charges go opposite the electric field, so the electric field actually points down. Okay, so the electric field points down, and that's what will make the force on this negative charge go up. Now, let's do the math here. Ultimately, we want to find what is the size of the spherical droplet. So we can solve for radius, we can solve for volume. I think solving for radius would be good here. And we can start by saying that the electric force, its magnitude, is equal to the weight. So E times Q equals mg. And this gives us the mass of the droplet. So the mass is the electric field, which is given, times the charge, which is given, divided by g. And we want to relate this to the size of the droplet. And a clue here is that it's telling us the density. So let's relate mass to size using density. We remember from last semester, density is mass divided by volume. We'll solve for the volume is mass divided by density. And over here, we have that mass is EQ over G, so let's plug that in. So the volume is EQ over rho G. And let's then plug in all the numbers. We have the electric field given. We have the charge. It's 3 times the elementary charge. And we're just keeping everything as magnitude, so we're not doing the negative here, divided by G, divided by the density, keep it all in MKS units. You should get a volume of 6 times 10 to the negative 19 cubic meters. Finally, we want to know the size. It's appropriate to give that either as radius or diameter. I'll give it as the radius. It's a sphere, so volume of a sphere is 4/3 pi r cubed. Solve that algebraically. R is the cube root of 3 volume over 4 pi. So you should get 5.2 times 10 to the negative 7 meters. Number 79. In an X-ray tube, electrons are accelerated in a uniform electric field and then strike a metal target. Suppose an electron starting from rest is accelerated in such a field directed horizontally with the given magnitude. The electric field covers a region of space 10.5 centimeters wide. What is the speed of the electron when it strikes the target? How far does it fall under the influence of gravity during its flight? All right, so question A is a one-dimensional, it'll become a kinematics problem. Question B is going to get into projectile motion where it's going to fall a little bit. So for question A, we want to know the speed it's going. We'll start with F equals ma, and the force on this charged particle is electric field times the charge equals ma. And we want to solve for acceleration. So acceleration is electric field times charge divided by mass. Now, if we want to know how fast it's going to be going, we'll use this kinematic equation. V squared equals V naught squared. It started at rest, so that's 0, plus 2a times delta x. which means v squared is, let's plug in what we got up here for A, 2 times, and for A we have EQ over M, and then don't forget the times displacement. And then we solve for that, don't forget to take the square root of v squared. So v is a speed of 9.22 times 10 to the 6th meters per second. Now, question B then asks okay, so how far does it fall under the influence of gravity during its flight? So as back in chapter 3 last semester, we treated projectile motion. Let's first find the time of flight. So we have its displacement. We know how far it went horizontally. It says 10.5 centimeters. And displacement is v naught t, but v naught was 0, plus 1/2 at squared. So to solve for the time in flight, we get the square root of 2 times displacement over acceleration. Remember that acceleration up here is EQ over M. And you may have wanted to back up here solve for the actual numerical value of acceleration. I didn't, but since I didn't, I've still got this term here. And you should get a time of 2.27 times 10 to the negative 8 seconds. And now you're going to see how far does something fall, anything fall, under the influence of gravity in this much time. And so we can use the kinematic equation in the y direction, which reduces to the distance it falls is 1/2 gt squared. We just solve for t, so we get 2.5 times 10 to the negative 15 meters, or 2.5 femtometers. Number 81. An electron is traveling with speed 2.1 times 10 to the 6th meters per second when it enters a uniform electric field that is parallel to its direction of travel. After moving for another 9.2 centimeters, the electron comes to rest. What is the magnitude of the electric field? What is the direction of the electric field relative to the electron's original motion? Okay, so this electron is going fast, and it's going to be slowed down. Let's just draw a picture right here. I've started by drawing the electron going to the right with v naught, and it's going to be slowed down, so its acceleration is to the left. Remember that a negative charge will be accelerated in the opposite direction of the electric field. So the electric field must be going to the right, so that the electron's acceleration will be to the left. Okay, so that's the direction of the electric field. Now let's figure out the magnitude of the electric field. We can start with electric field is F over Q, and F equals ma, so the electric field is ma over Q. We don't at the moment know acceleration, but we'll use kinematics to figure this out. We know v naught, we know v, we know that it came to rest within a displacement of 0.02 or 0.092 meters. So we'll use this equation to solve for acceleration, just like we did back in chapter 2 last semester. And you should get an acceleration of negative 2.397 times 10 to the 13th meters per second squared. Once you know that acceleration, let's plug it into what I got up here for electric field is ma over q. So ma, a being negative, q is negative, E is going to turn out to be positive, which is good because that's what we found here. It's in the positive direction. You should get 136 newtons per coulomb. Number 89. As they fly through the air, honeybees can pick up a small amount of electric charge. Suppose a 0.12 gram bee acquires a charge of negative 55 picocoulombs. How many excess electrons has the bee acquired? Find the electric force on the bee in the electric field just above Earth's surface, 120 newtons per coulomb directed vertically downward. Compare your answer in part B to the bee's weight. All right, so I have the given information, the mass of the bee, the charge, and we want to find how many electrons this is. So we'll take negative 55 times 10 to the negative 12 coulombs multiplied by 1 electron over negative 1.602 times 10 to the negative 19 coulombs. And so you should get that it's picked up 3.43 times 10 to the 8th electrons. Now, question B asks, find the electric force on the bee in the electric field from the Earth, assuming that, going back to the given information that it's picked up that much charge. So the forces on it are going to be upward because the electric field is going downward. It says directed vertically downward. So F equals EQ. We have the electric field given, negative 120 newtons per coulomb, and I call it negative because it's downward, times the charge, which is also negative, and it gives that upward force, just as I've drawn in the picture, of plus 6.6 times 10 to the negative 9 newtons. So this bee, having acquired these extra charges, actually has a bit of a levitation force, something that's going to lift it up, kind of like a buoyancy force. And now the next question essentially asks, is it a negligible force? Is it worth anything compared to the bee's weight? Question C says, compare the answer. So a good way to compare is to find the ratio between the two, the ratio of this force to the bee's weight, or the bee's weight to this force. The bee's weight is its mass times g, 0.001176 newtons. So let's find a ratio of its weight to the electric force. Weight over the electric force is 180,000. So even though there is this bit of a levitating force on the bee, its weight is 180,000 times more than that force. So essentially the force is going to be negligible. And that is the end of the Chapter 15 homework. Have a great day.